Yeah, hi all. Very good evening and welcome back to the ninth week of the TA live sessions for artificial intelligence search methods for problem solving. Um, so before we get started, can you all hear me properly and is my screen visible? Okay, great. Thanks for the confirmation. Um, yeah, so this is the ninth week and we'll be continuing discussing some questions on planning. And so last week we discussed some of the possible algorithms to solve planning problems. Today we are going to see a few more of them and some other methods also we are going to see. Basically some other methods, some other questions based on these planning methods. Okay, and I did see that there were two requests in the discussion forum, but I haven't been able to go through the exact questions that were requested. So we'll see in the end if we have time, we'll discuss it today. Otherwise, we'll probably discuss it next week. So yeah, but before that, let's first discuss the questions for this week from week 9. And yeah, let's get started. Yeah, so the problem setting that we are going to use for planning would be the same as the one that we used in the previous live session, which is the one jab, two jab, and uh, getting vaccinated at the hospital and then attending a particular event. So, is there anyone who needs a refresher on this particular problem setting who could not attend the previous one? Okay. Uh, yeah, I see a hand raise. So, if you have a doubt, you can speak up. But if you meant to say that you missed this particular problem setting, then let's briefly go over it for the sake of continuity. All right. So basically, we have a set of predicates defined. Okay, each of these means something specific. So we have something like at x comma location. This x is a person. Okay, and this basically means that x is at a particular location that is given by this LOC or loc. Okay, this could be a hospital, this could be a event, concert, railway station, anything. Okay, hospital appointment X. This is the next predicate, which basically means that X has an appointment in the hospital. And then no jab X. So jab basically refers to a vaccine dose. This predicate basically means that this person X has not got any dose of vaccine. Similarly, one jab X means that this person X has got one dose of vaccine, and two jab means that this person has got two doses of vaccine. Then the second last predicate is the ticket X comma event, which basically means that X has a ticket for a particular event, which could be a concert, a flight, or a train. And the last predicate is attending X comma event, which basically means that X is part of this event or X is attending that event. So these are all our predicates. Now let's have a look at the different operators that we are going to deal with. So each of these operators, for us to be able to apply these operators, um, we need certain preconditions to be satisfied. Okay, so for every operator, we'll have certain preconditions. Like for this one, we have no jab X, hospital appointment X, and at X comma hospital. And each operator will have certain negative effects and certain positive effects. This basically means that if you are in a particular state that is defined by a given set of predicates or facts, application of a particular operator will remove some of those facts from that state and add some new facts to the state. The facts that are removed are basically constituted in this negative effects, and the facts that are added are constituted in this positive effect. We have some six operators given to us, basic which each of them referring to something different. The first one, for example, refers to X getting a certain dose of vaccine. The second one refers to X getting the second dose of vaccine. Then the third one refers to X getting an appointment to a hospital. This go X comma hospital refers to X going to the hospital physically. Then the fourth predicate refers to, or the fifth predicate refers to X booking the tickets for a particular event. And the last predicate refers to X attending that particular event. Okay, each of them has some preconditions, some negative effects, and some positive effects. And then again, we are going to begin with the same initial state that we were told. Okay, we have a certain set of facts given to us about three different individuals. One is Amol, one is Anisa, and one is Aisha. Okay, so for Amol, we are only told that Amol has 2 doses of vaccine already. About Anisa, we know that Anisa has 1 dose of vaccine already. And about Aisha, we know that Aisha does not have any dose of vaccine. And additionally, we also know that Aisha is at the hospital and Aisha also has an hospital appointment. Okay, so we know 3 facts about Aisha, 1 fact about Anisa, and 1 fact about Amol. And our goal is to reach this particular state. This is the final state that we want to reach, where each of these 3 individuals are attending an event. That event is a concert. Okay, so we need to apply a set of operators step by step so that each of these individuals uh, start attending that event, or each of these 3 predicates become true. Okay. Okay, any doubts about this particular problem setting? Okay, yeah. So a couple of uh, doubts in the chat box. So, okay, so we will cover AO star algorithm with an example later down the line today. So we'll address that then. And then, okay, so I see a number of you are telling that you are facing problems to solve the assignment question, which is the blocks world domain. Um, what we can do is, uh, uh, so let's continue discussion with this problem setting, and in the end, we can have a brief look at what this blocks world domain is. Maybe we can have a brief discussion on that, and maybe that will help somewhat to solve the particular practice or assignment questions. Okay, because see, essentially the methods are the same, the algorithms are the same. We just have to spend a bit of a time to understand what the predicates are, what they imply, what the operators are, what they do and what they don't do. Okay, so sample solution for block world, I don't have any sample questions for block world. Okay, so if I'm so that's why I'm saying that we can maybe continue with this particular problem domain, and then maybe in the end, if we have time, we can have a look at the question that was given into you in the previous week's assignment and see if we can get some clarity on the block world domain or the block world problem setting. And yeah, if time remains, we can even try to discuss the solutions. Could we do practice assignment in the session that would cover the block world? Yeah, sure, that would be great. But again, yeah, okay, let's see. If we have time, let's try to cover one of the uh, uh, practice questions that deals with block world. Okay, but for now, maybe let's continue with this because the assignment has been, or the live session has been planned with this particular problem domain. Um, okay, so an extra session for FSSP, VSSP, also for GSP. Um, okay, let's see. Let's to I see all of your queries, but uh, let's first complete all the questions for today, and then let's move on to whatever additional queries we have to discuss. Okay, would that be okay with all of you? Okay, great. Okay, so as of now, is this particular problem setting clear? Okay, that's good. Fine, then let's move on to the questions for today. All right, so the first question is about this method called graph plan. Okay, all right. So the question says that we are given a set of actions, okay, among these different options below. From the set of actions given below, what are the actions that will be present in the first layer of the planning graph that will be constructed by the graph plan algorithm? Okay, so let me do one thing. Since graph plan slightly borrows some concepts from FSSP, let me briefly go over it once more. Okay, so maybe that will address a part of your queries. Okay, so in forward state space planning, what we do? So we are given some particular state, okay, which has a certain set of facts. Let's say fact 1, fact 2, fact 3, fact 4. This could be anything, okay, any of the predicates. Like some initial state we had, this is some other initial state, some general initial state, okay. And we also have in the side, let's say, we have a set of operators, okay. Let's say we have some operator op1 that has some preconditions, some negative effects, and some positive effects. Similarly, we have some other operators up 2, up 3, up 4, so on and so forth. Okay. Now, each of these operators requires some preconditions to start with or to work with. Okay. And what those preconditions are? Those preconditions are basically some subset of the different predicates that could be possible in this problem setting. Okay, so what you will do is that you will have a look at your given state. Okay, you'll start with the initial state. Okay, you'll see that whether any particular subset of these different predicates or these f1, f2, f3, f4 that is given to you is satisfying the preconditions of any of these operators. Okay, it might be the case that on one extreme, it might be the case that different subsets of these f1, f2, f3, f4 satisfying the preconditions of all your given operators. Okay, and another extreme could be that uh, these particular only the some subset of these particular facts in the initial state is only satisfying the preconditions of only one given operator. Okay, so depending on, irrespective of how many preconditions, how many operators precondition is satisfied, you will list down all such operators that could be applicable given these set of facts. Okay, so maybe let's say that the first operators requires f1 and f2 as precondition. Okay, so operator 1 will become one of the possible operators you could apply. Let's say operator 2 required only f3 as the precondition. So operator 2 will become another possible operator that could be applied. Let's say there is another operator called operator 3 that requires f4 and f2 as its preconditions. Okay, so operator 3 will become another possible operators that you could apply. And let's say we have another operator called operator 4 that requires some other fact, let's say f5 to be as its precondition, and that f5 is not a part of the initial state. So operator 4 will not be a possible operator that you can apply as of now. Okay. So let's say these three are the operators that you could apply. So this is basically what forward state space planning does. Given a particular state, it lists or it makes the, so every node is defined by a state. Okay, and the children of that state are the operators that you could apply given the facts in that particular state. Okay, these operators may be redundant. Okay, for example, it may be that once you apply operator 2, you end up with nothing but fact 3 again, which is already a part of your initial state. Doesn't matter. Forward state space planning will list all possible options that you could go for. Okay. Similarly, it might be that operator 1 uh, uh, lands you in a state where you do away with your f1 and f2. So f1, f2 are no longer part of your state. f3 and f4 are still there, and maybe application of operator 1 adds this fact called f5. Okay, so now your operator 4 will become applicable from this state onwards. Okay, this will be your next state if you applied operator 1, and now you could use this f5 fact to say that operator 4 is one of the possible operators you could apply. And similarly, you could continue with the different operators that you could apply given F3 and F4, let's say operator 2 and operator 3 maybe cannot be applied because operator 3 we said that requires F2 and F4 and you only have F4. So op4 and op2 are the two operators you could apply, and you will proceed so on and so forth for each of these next states that you arrived at. Okay, so this is how your tree will keep on growing until you reach some state that contains, let's say, after filling in your trees for a certain number of levels, you reach a particular state where each of your goal, each of the predicate in your goal state has been achieved. Okay, when these three have been achieved, let's say you have to satisfy only three goals, three sub goals, then you will say that according to some plan starting from the initial state, following some steps of applications of different kinds of operators, you have reached a state that satisfied your goal, and so you have found a plan using forward state space planning. Okay. Um, so does that help slightly with any doubts regarding FSSP? Anyone? Yes, no, anything? Okay. Thanks for the confirmation. So one person confirmed. Okay, so let's proceed, and let's hope that it's slightly more clear. All right. So are some of you familiar with this graph plan algorithm? Have you gone through the week's lecture videos? Okay, so that's great. Some of you are familiar with the graph plan algorithm. Then I'll give you a bit of time. So it might be a bit too tedious to work out the whole of it on your own just right now. So I'll just tell you to draw the just the first action layer. Okay. Let's try to draw the first action layer only, and then let's have a discussion because that's what is asked in the question. Okay, the question asks what are the actions that will be present in the first layer of the planning graph that will be constructed by the graph plan algorithm, right? So you try to draw the first layer itself, and I'll give you a couple of minutes for that, and then we'll have a look at the solution and we'll discuss how we arrive at that. Okay, and remember that FSSP is something that you will try to use while you're trying to construct this particular planning graph. Sure, yeah. The initial state that you're going to start with would be this. Um, yeah, so thanks for your message in the chat, Dr. Preeti. I can try to get it uploaded to upload it myself today, but it will be slightly difficult. But yeah, I'll try my best. If not, tomorrow morning for sure. Yeah, sure. I'll try to upload it tonight. There's a question in the chat box how to know that it was the first layer. So you'll proceed. So you'll start with a given set of predicates, right, which is your initial state, and then you'll try to construct the first layer of your action set, right, which is basically the actions that you could apply given the predicates in your previous state, right? The predicate state. So this initial state will be your P0. What the question asks is that you have to construct A1, which is the first layer of the action set. Okay. So Lokesh, all this information is available in the Swayam portal. So if you go to the problem solving sessions section in the Swayam portal, you will find all the information about the channel name, the drive folders, the individual week recording links, everything is there. All right, so yeah, you can take a couple of more minutes and yeah, I'll shift back to the question maybe. And yeah, after a few minutes, we'll try to discuss the solution. All right, so I see that some of you have already given the answers. So let's start with discussing the solution and maybe we'll see how to proceed. Okay, so if you remember, this was the optimal plan that we had discussed in the previous session. Now we'll try to use graph plan and see how whether the results change or whether we get the same information. Okay, so let's first write down our initial state. So we were given that Aisha does not have any shots of vaccine. Um, then what were the other predicates? Let's just quickly have a look. Yeah, we had 1 jab Anisa, 2 jabs Amol. So let's write that down. Okay, and the other information that was given to us was that Aisha is at the hospital and Aisha has a hospital appointment. All right, so these are the basically information that is given to us. We will call it our P0. Okay, and what we have to do is we have to construct the set of actions in the first action layer. Okay, so basically what graph plan does, it constructs consecutive or uh, yeah, layered, basically different layers, alternate layers. The first layer starts with a set of predicates that are defined as the initial state. The next layer is the set of actions that you could apply given this particular set of facts. The following layer is again called P1. Okay, which basically constitutes the set of facts that follow as a result of the different actions in this particular action layer. Okay, so first we have to construct the action layer and then we can construct the P1. Okay, okay, so let's see. So there are different operators we could apply, right? Let's first consider the case of a mole. Okay, so first of all, there is a special operator, okay, that is used to copy facts directly from one particular predicate state to another predicate state. And this operator is called a no-op operator. That is something specific to the graph plan algorithm. Okay. So this is something that might not be defined also in your normal problem setting, but this is something that you can use when you apply your graph plan method. Okay, so basically what this does is it takes a particular fact from a given state, a particular predicate state, and it simply copies it to the next predicate state. Okay, so here you will have something like no jab Aisha. Let me actually write it in text. Okay, so if you had to define this no operator, it would be something like it takes as precondition this particular fact. Okay, so this no op, and there could be multiple no ops. Okay, so this particular no op one, let's say, the preconditions for this one would be this fact, no jab Aisha. That would be the precondition. Okay, the negative effects would be nil. Okay, because this is not having any negative effect. It's not removing any fact from your set of facts. The positive effect would be addition of the same prerequisite condition to your next state. Okay, so this would also be no jab Aisha. Okay, so this is how you will define your no op operator, and this is just an example for one fact. You could have individual no op operators for each fact you want to copy from one predicate state to the next predicate state. Okay, all right, so this is one example of a no op operator. Now let's go back to and see, look at each of these individuals one by one and see which are the different operators we could apply. Okay, so for Amol, we know that 2 jabs Amol is the information given to us. And if you remember from the uh, different questions we discussed last week, uh, the two operators that would be applicable for Amol, given this small information that Amol has 2 jabs of vaccine, would be, can someone tell which two operators would be applicable in case of Amol? Yeah, that's right. Get appointment and book. Okay. Okay, so I see there were a few messages in the chat. So which part did you miss exactly, Rocky? If you could tell us that, we can go over it once more. By the way, if you have any question, you can feel free to unmute yourself and speak up. You don't have to raise your hand every time you want to ask a question. Okay, just reiterating that. Okay, from the action layer. Okay, so the action layer we just started constructing. So action layer will basically constitute all the actions that you could apply given your initial state or the previous state, which is the predicate state. Okay, so we just discussed one particular kind of operator that is specific to this graph plan method, which is called a no op operator. Okay, and this what this basically does is that it copies the facts or the predicates from one layer to the next layer. Okay, so it's just taking this no jab Aisha fact, it's not doing anything about it, and it's simply copying it to the next predicate state. That's all this no op does. Okay, this is just one example of a no op operator. You could have such individual no op operators for each of these facts given in the initial state, which also basically implies that you will never reduce the number of facts uh, that you have as you move progressively in the different layers through the different layers of the graph plan method. Okay, and that in turn will give rise to different contradictions that will come up later when we discuss the method. Okay. Okay, so yeah, as some of you said that the two different operators that we can apply uh, given this particular set of facts in the P0 layer for a mole, those are get appointment to the hospital and to book the events for the ticket. Book the ticket for the event, sorry, the other way around. Yeah, so let's write down our those two actions in our action set. Okay, so I'm not writing the whole thing. This is okay, give me a moment. Yeah, sorry about that. Yeah, so basically this will be one of the action that we could apply, and the other will be book a mole concert. Right? These are the two actions that we could apply for a mole given the um, set of facts to us. And how do we mark the preconditions? So let's use yellow to mark our preconditions. Okay, so this get appointment does not require any prerequisites, right? If you remember from the set of operators, this um, get appointment has nil prerequisites. Okay, so we don't need to mark anything as prerequisites, but um, it has one positive effect, and let's mark the positive effects with the blue line. And the positive effect would be that Amol has an appointment for the hospital. Okay. All right. So this is one positive effect. Let me actually make it better. Okay. Similarly, this book Amol concert, what does this require as the prerequisite? The preconditions. This requires two jabs X as the precondition. It has no negative effects, and it has one positive effect. which is that Amol now has tickets for that particular event. Okay, so we will draw one line from this 2 jabs Amol to this particular action, which is book Amol comma concert, and then another predicate will be added to P1, which is um, okay, this will be the positive effect of this particular action. Let's mark it with our blue edge. Sorry about that. Okay, so this was for Amol. Now let's consider Anisa. What are the different actions that we could apply for Anisa? Okay, um, that's right. Get appointment is one action that we could definitely apply because that does not require any prerequisite. So let's write that down. And one of the positive effects of this would be that Anisha would now have a hospital appointment. Okay, let's mark the corresponding edges. It has no prerequisites, but it has one positive effect. Okay, is there any other operator that we can apply? I think if we remember correctly, then there were 5 such operators that we could apply for Anisa, right? Or was it not the case? Let's maybe check with the previous session slides. Okay, we have the previous session slides with us, so let's go and check. Yeah, maybe we couldn't apply 5 operators. That was something else. That was, I think, the length of the plan, not the number of operators. Yeah, for Anisa, there's only one particular operator we could apply, that is get appointment. Okay, that's great. Now, what about Aisha? For Aisha also, we can directly say that get appointment Aisha will be one operator that we could apply. So let's straight away write that. Okay, what will be, so go Aisha comma hospital will also be a particular operator we could apply, right? Because we are already told that Aisha has an hospital appointment, so we could use this go hospital operator to apply that as well. We could also apply this get jab one operator, right? Because we have no jab Aisha, hospital appointment Aisha, and at Aisha comma hospital given to us. So we could use these three. Oops, sorry, I might have given you a hint about the final solution. But anyway, okay, so I'm not drawing the precondition and the positive effect arrows for all of these. Let's focus on this get jab 1 Aisha. Okay, because I want to convey the point about mutually exclusive operations. So let's consider that. So this get jab 1 requires three preconditions, right? One of them is no jab Aisha. Okay. Another one is at Aisha comma hospital, and another one is hospital appointment. So this has three edges coming into this particular action, which is get jab 1. Okay, what are the positive effects of this particular action? The positive effect is that we have one jab Aisha corresponding as compared to no jab Aisha. Okay, so that is the positive effect of this particular operator, but um, this operator also has some negative effects, right? And those negative effects were no jab X, no jab Aisha, hospital appointment Aisha, and at Aisha comma hospital, which basically means that let's first add those facts in our next predicate layer. So we already have no jab Aisha, right? So another one would be at Aisha comma hospital, and okay, so there will be some negative edges. Let's mark those negative edges with red. Okay, so get jab 1 will have this as a negative edge, it will have this as a negative edge, and it will have this as a negative edge. Okay, so here you see that you have one example of where one particular action, this no op action over here, let me use a different color to show that. Let me use the laser pointer. This no op action is creating some positive effect, which is no jab Aisha. Okay, and there's another action get jab 1 that is creating a negative effect, that is also no jab Aisha. Okay, so you see an intersection of the blue line and the red line for one particular predicate, and that is an example of contradiction. Okay, so you will say that these two actions are mutually exclusive. Okay, so let's mark these mutually exclusive actions with the help of a zigzag line. Okay, so this get jab 1 Aisha action and the no op action over here, these two are mutex or mutually exclusive. Okay, this is one possible example of mutex operators or mutually exclusive operators. If you see the lecture slides and the lecture videos, Professor Khemani has gone into a detailed discussion about how we can arrive at different actions that are mutually exclusive. Okay, so I highly recommend you revisit that. That might cover some cases that we may not be able to cover through the example. Okay, yeah, so just go through that before you answer the question or the questions for your assignment. But yeah, that was an example of mutex operation, mutex actions. Okay, so Abhishek, yeah, I understand that mutex is a bit confusing. Let's go over it once more. So basically what I'm saying is that you have one particular action over here that is creating some uh, positive effect in this next predicate state. Okay, this is your next predicate state. Okay, that is, so there is one action that is creating some positive effect. Okay, and there is another action in your action set that is creating a negative effect, and that both of them correspond to the same predicate, which basically means that one action in the action set is trying to add this particular predicate to your predicate state, and there is one action in the action state this one that is trying to remove it from your predicate state. Okay, so you see that there is a conflict over here. One action is trying to add it, one action is trying to remove it. So there we say that these two actions, this one action and this one action that are conflicting, they are mutex, or they are mutually exclusive, which basically means that you cannot apply both these actions at the same time in your plan. If you apply these both these actions at the same time in your plan, it will lead to a contradiction and you won't be able to move ahead in your plan. Okay, so whenever you complete your planning graph, you have to make sure that you don't choose two mutually exclusive actions as part of your plan in a particular step. Okay, so this was just one example of a mutex operators. Okay, right. So yeah, you're right, Rocky. This is just one example of a of a pair of mutex operations. There can be other mutex operations as well, and I'll encourage you to try to find that for this particular action one layer. And I'll give you some time, and then we can have a discussion, or we can have a look at the solution that I've already constructed. Then we can see how many mutex pairs we could find in this action layer. Okay, so I'll give you a couple of minutes for that, and then we can move on to the next one.
Hello.
Yeah, Shanti, please go ahead.
So good evening. I have little doubt. IS is nothing but the initial state that was given in the question, and the middle part is actions that is considered, and the third one is positive and negative effects. Both we are writing. So we are taking one initial state. How the middle part is filled based only on the preconditions. If precondition is satisfied, that actions is only mentioned, or all possible actions is mentioned in that middle part, sir.
So you have to you can write all possible actions that you can apply, including the no op actions, and then so this is what graph plan does. Okay, it makes these alternate layers of actions and predicate layers that can contain all your possible set of actions that you could apply. And then once you have reached some state in your one of your predicate layers that contains your goal state, that you goal predicate that you want to reach, then you'll trace back your steps. Okay, and in each action layer what you'll try to do is you'll keep track of the mutex actions, this mutually exclusive actions. So when you trace back from your final predicate state, you'll make sure that you don't choose any mutually exclusive actions at a given action layer. Okay, so this is just the first action layer. After P1 there'll be an A2. Okay, after A2 there'll be a P2, and you'll go on doing this until you reach a predicate state that has your goal condition or the goal predicate. Okay, and then you will try to trace back your steps to see which are the actions that you could follow starting from the initial state that could lead you to this particular goal predicate. Okay, and while doing that, since you have already kept track of the different mutually exclusive actions in each action layer, you will avoid those. That is the idea. But yeah, this plan that we have drawn as of now, that you can see, this is an incomplete plan. Okay, so yeah, you are supposed to write down all possible actions you could apply.
Okay, thank you, sir. That yellow one you marked. What you
Uh,
said about that, sir? The middle A1 part, actions part.
Yes, the yellow operator that you can see, that as we were discussing earlier, that's a no op action. That's a something.
What, sir? Please, can you say what is that no of action, sir?
Yeah, I am about to say that. So basically, this is something that's a characteristic of the graph plan algorithm. This graph plan algorithm allows you to use this no op operator to just copy one predicate to the next predicate state. Okay, it basically means that if there is some particular predicate in your previous predicate layer, that's a p0, that is not getting added to the next predicate layer p1, let's say, and you want it to be added, you can use this no op operator to copy that predicate from p0 to p1, or any p.
But it do not have any actions. P not. Why no job Aisha is directly going for P1, sir? No preconditions means we can go like that.
Yeah, so this no op has only one precondition, which is the predicate that you want to copy.
Okay.
Yeah,
Okay, sir.
yeah,
Thank you so much.
sure. Okay, yeah. So a couple of questions in the chat box. Good question, Vanshika. So yeah, we have noted down a partial plan where we were focusing on Amol first, and then wrote down one particular action of Anisa, and then we wrote down the possible actions for Aisha. So since these three goal states that we want to reach, the three goal predicates, these are independent of each other, right? The three agents, Amol, Anisa, and Aisha. We could make plans for each of these three individually, so you can construct your graph plan algorithm, this graph or this basically this graph that you want to planning graph that you want to construct. You can make it for each of these agents, the Amol, Anisa, and Aisha, separately or together. Okay. Uh, in what we have drawn all of them together itself. Okay, we have considered all so this particular layer A1 is not specific to Amol or Anisa or Aisha. It contains the possible actions that you could apply for all three of them. But if you want to draw a separate planning graph for Amol or Anisa or Aisha, you could do that as well. Given the final goal predicates that you want to reach are independent of each other. Sure. So basically, the final planning graph that we are going to have a look at, that will be separate for each of these three individuals. Okay, so maybe that will clarify your doubt, Vanshika, when we have a look at that particular solution. So just let's wait for a couple of more minutes, and to address your query, Abhishek, yeah, we'll have a look at the mutex operation just in a while. And Ram, yes, yes. So no op is basically a operator that we have come up with, or graph plan algorithm allows us to come up with, that simply copies one fact or one predicate from one predicate layer to the next predicate layer. Okay, it has only one precondition, which is the fact that you want to carry forward to the next predicate layer. It has no negative effect. It has only one positive effect, which is the fact that you want to copy to the next predicate layer. Okay. All right. So now let's have a look at the solution that I have already constructed. Okay. So following our convention, I have marked these. So the yellow color is used to mark the precondition or the precondition pre-requirements edges. Okay. Blue is used to mark the positive effects. Red is used to mark the negative effects. This zigzag line is used to mark the mutually exclusive actions, and this yellow kind of rectangle with an incoming yellow edge and an outgoing blue edge marks the no op action. Okay, so here if you see that we have 5 pairs of mutually exclusive actions. Okay, so let's go through each of them one by one. So first so there's one no op action which is copying this fact no jab Aisha from this P0 to P1. Okay, so if you see that there's a yellow edge that's going into this no op operator, and it has having one positive effect, which is no jab Aisha again. Okay, so it's simply copying this no jab Aisha fact from P0 to P1. That is what this no op action does. Okay, now we have another operator get jab 1 Aisha that has as its preconditions three edges. So it has three incoming yellow edges. One is no jab Aisha, one is at Aisha comma hospital, and another one is hospital appointment Aisha. Okay, so it has three incoming edges, which are basically the three preconditions that we need for this operator, and it has one positive effect, which is one jab Aisha. It has three negative effects. Okay, so those are marked by these red edges. Okay, so one of the negative edges is no jab Aisha. Another negative edge is at Aisha comma hospital, and another negative edge is hospital appointment Aisha. Okay, so now since we see that there is one fact over here, this no jab Aisha in P1 predicate layer 1, which has an incoming blue edge and an incoming red edge, which basically means that there is some action in your A1 action set that is trying to uh, add this particular fact as a positive effect, and there's another action in your action set that is trying to remove this particular fact as its negative effect. Okay, so there is a contradiction over here. That's why we have added this mutex edge between these two, this no op action and this get jab one Aisha action. Okay, similarly, I'll give you an example of mutex relation between two actions that are not no op. Okay, let's consider again this get jab one Aisha. This is one operator, and then this go Aisha comma hospital is another action, another operator. Okay, so this go Aisha comma hospital, the one that I'm circling around, that requires as a positive edge or a precondition edge. Sorry, not a positive edge. It requires as a precondition this fact hospital appointment Aisha. Okay, so it has a yellow edge incoming from hospital appointment Aisha till go Aisha comma hospital, and it has as a positive effect at Aisha comma hospital. Okay, but this get jab one Aisha has a negative effect at which one? At Aisha comma hospital. Okay, so again you see that there is a confluence of red edge and blue edge at this point, at this particular fact. Okay, so again you'll say that there is a conflict over here, and this get jab one Aisha operator and this go Aisha comma hospital operator, these are in contradiction with each other. So we have added a mutex relation over here. Okay, so this also addresses the redundancy that you used to see in your FSSP algorithm. Okay, yeah, FSSP used to add the redundant actions as well as part of your tree. But here we are, since we are keeping track that ketchup one Aisha and go Aisha comma hospital are both mutually exclusive actions, we know that we shouldn't apply both of them at the same time step. Okay, so here you see that there are 5 mutually exclusive pairs. I'll give you a couple of minutes to go through each of them and convince yourselves. Okay, you want me to explain again? Okay, let's go through this once more. Okay, so see, when will mutex happen? Okay, focus at the set of facts given in this P1 layer. Okay. Okay, first of all, is it clear how we arrived at A1 layer? Let's move step by step. Is it clear how we arrived at A1 layer? How did we arrive at the actions in the A1 layer? Is that clear to everyone?
Sir, is it the graph is built based on a problem statement or it is given?
You have to build the graph given your problem statement.
Then let's start with the question statement.
We did start with it, right? You are
Yeah.
you are given your initial state, which is P0. Now you have to make your first action set, action layer 1, based on your P0.
Okay. The day one is we
A1 is
create.
the set of actions that you could apply given the set of facts in P0.
That's the part of the answer. It is not given, is it?
Yes.
So how did we really come on the list of actions? What is the basis?
So did you join the session a bit later?
Uh, Probably 5 minutes late.
So
Yeah.
yeah, so we will apply the
If it has
same.
been given already, then I will just watch the YouTube and pick it up from there.
Sure, no
Since you're
worries.
repeating it, it's always better from problem statement to the action statement. How did we really reach over there?
Yes,
Quickly,
so
you can
so
just
I'll
brush it up.
yeah, I'll just tell. Uh, so basically, we will apply something with something similar to what we did for FSSP method in the previous week, right? Given a set of facts, we saw which subsets of these different facts we can take as preconditions and see which of these preconditions for different operators are being satisfied, right? And then we list all of those. That's what we do over here as well. And the only addition is that we have additional no op actions as well.
Okay.
Yeah, that's what we do. So, okay, so if it's clear how we arrived at A1, now let me ask you, is it clear how we arrived at P1 now? Okay, that's great. Basically, the way we arrived at P1 is um, we enlisted all the facts that we want to carry that are positive effects of the different actions in your action set. Okay, and this also might happen to have facts that are a negative effect of some of these actions, right? So how do we differentiate between those two? Then that is where we use the negative edges and the positive edges. So the blue edges are the ones that mark the positive effects of the different actions, and the red edges are the one that mark the negative edges of the different actions. Okay, so is the concept of the different coloring of the edges clear? The yellow edges mark the preconditions for each action. The blue edges mark the positive effects of each action, and the red edge marks the negative effect of each action. Is it clear until that point?
Yes, sir.
Okay, that's great. So now what I'll request you to do is take a look at the set of facts or predicates in your P1 layer and see if there is any fact that has an incoming red edge as well as an incoming blue edge. Can you identify facts like that in P1? Anyone?
Get jab, Aisha. Then red and blue is combined
Yeah.
from same location.
No. So I'm asking you to look at the predicates in the P1 layer. Okay. Look at the facts in the P1 layer. Let me show you this layer. Look at the facts in this layer and then see which of them have an incoming blue edge as well as well as an incoming red edge. This is one such fact, right?
No jab, Aisha. Yeah.
Yes. So basically, what this means is that there is one action from which this blue edge is coming that is trying to add this fact because of a positive effect of that action to your P1 layer. Okay. You agree with me?
Yes.
And there is some other action that is trying to remove this particular fact from your P1 layer because you have a red edge incoming from that action. Do you agree on that?
Yes.
Which basically means that there is a contradiction over here. One of your actions in your this A1 layer is trying to add this fact. Another action in your action layer is trying to remove this fact. So ideally, you would not want to apply both these actions at the same time, right? Because then it would lead to a confusion and contradiction in your plan. Do you agree with me?
Yes, sir.
Exactly. That is what is indicated by your mutex relations. So different actions in your A1 layer, different pairs of actions in your A1 layer that have that kind of a contradiction going on, they are classified as mutex actions. Okay. So here if you see that no jab Aisha was one such example of a fact that led to mutex relation between this no op operator and this get jab one Aisha action or operator. Similarly, see that this at Aisha comma hospital, this is another fact that has incoming blue and red edges or incoming positive effect edge and incoming negative effect edge. Okay, so there is one red edge that is coming from get jab one Aisha, which basically means that get jab one Aisha action is trying to remove this at Aisha comma hospital from your predicate set P1 set. But there are two different actions. One is this go Aisha comma hospital action that is trying to add this predicate to your P1 set. So you would say that there is a mutex relation between get jab 1 Aisha and go Aisha hospital. There is another positive edge that is incoming to your at Aisha comma hospital. Okay, which is basically a positive effect of this no op action, that is simply copying this at Aisha comma hospital fact from your P0 to P1. So you'll also say that there is a mutex relation between this get jab 1 Aisha and this different no op operator, that is copying this at Aisha hospital back to your P1. Okay, so as of now you arrived at three pairs of mutex relation. One was this one was this one, and another one was this one. Okay,
Excuse me, sir.
sorry, was there any doubt?
Sir, is it proposition layer or not?
Uh, can you please come again? I'm really sorry, I couldn't hear you properly.
Sir, no jab Aisha.
Uh-huh.
Is it the proposition layer or not?
It's a predicate layer. Okay, you're dealing with predicates over here, which you can say that all these are different fact layers.
Okay, sir.
Yes, so in graph plan algorithm you will have alternate layers of, so you will start with a particular set of facts, okay, that you will call your uh, P0. So P basically means you were given a set of predicates to begin with, right? Which basically gives, you can say that these are different facts that are given to you. So this P basically indicates that only. Okay, so you're starting with P0, okay, which is your initial state. Then you are forming your A1, which is A basically means action. Okay, A refers to action or operator. Here you have listed the different operators you could apply. Now P1 is the next predicate layer that contains the different predicates that you have carry forwarded from P0 using the no op actions, as well as the predicates that are a result of the positive effects of different actions that you are applying in your A1 layer. Okay, this this graph plan algorithm is not something that you are implementing. Okay, this is part of your planning. Once you have completed drawing the whole graph plan algorithm, that's when you'll start constructing your final plan. Okay, so just mentioning any action over here doesn't mean that you are actually applying it. You are just enlisting all your different options over here. Okay, does that help? Is the concept of mutex operators somewhat clearer now? Okay, why is hospital appointment Aisha no op? Okay, before that there was another chat message that said no jab Aisha at Aisha, comma hospital and hospital appointment Aisha. Yeah, I suppose you were mentioning the ones that led to contradictions or mutex relation, and you're right, Rocky. Yeah, that's right. These are the three facts in P1 that give us the different mutex relations in A1. Now coming to your question, Ram, why is hospital appointment Aisha is no op? Um, so yeah, so that is no op because you chose to copy it from your P0 to P1. Okay, so for the sake of thoroughness, see that this hospital appointment Aisha is also a result of this get appointment Aisha. Okay, it has also a blue edge coming from a different action, which basically means that your A1 can contain multiple actions that result in the same fact, and it can also contain different actions that try to remove the same fact. Okay, you're basically trying to list down all your different options. Okay. Any confusions as of now? I'll give you a few more minutes to go through this part of the planning graph, and then we'll have a look at the complete planning graph. Okay. Yeah, so as your colleague is mentioning over here, that you can copy or carry forward each predicate in P0 to your P1 layer using the no-op operation. Okay, so let's wait for maybe 2-3 minutes, and then let's move on to the final graph, the planning graph that we'll see for the graph plan method. And when we see the final planning graph, that will be separate planning graphs for each of the three individuals, Anisa, Aisha, and Amol. So mutex lines are basically, we are marking those zigzag edges between operators that are leading to contradiction in your next predicate layer. Okay, so if you have a fact in your predicate layer that is positive effect of one action and at the same time a negative effect of another action or more than one actions, then you say that there's a contradiction, and you mark those pairs of actions as mutex or mutually exclusive. That's what these mutex lines indicate. And if you'd like to have a further detailed explanation for that, you can revisit the video recordings once it's uploaded back.
So why is it named as mutually exclusive?
So
When there's a
mutually,
conflict is coming, then what is that what is the mutual exclusive thing happening there?
sure. So basically, if you remember from, I'll give you a simple example from set theory. Okay. So if you have some set, let's say this is one set A. Okay, this is another set B. If they have no overlap, nothing in common, you call them to be mutually exclusive, which basically means that they don't have anything in common, right? Or there cannot be that if you had something like this, where you have some intersection, you say that they are not mutually exclusive. You
Okay.
apply this an analogous logic to this problem again. This problem also, when you say that a pair of action is mutually exclusive, you basically mean that you cannot apply both of them together. There is no overlap between them, or they can't go hand in hand. This is what is basically meant by mutually exclusive. Does that address your query?
Yes, sir.
Okay. Okay. Now, yeah, thanks for your message in the chat box, Rocky. I hope that this part of the planning graph is more or less clear to everyone. So here we were trying to form the planning graph for all of them, all Anisa, Mole, and Aisha together. Okay. Now let's look at the full planning graph for each of them individually. The reason that it's advised to draw the planning graph for each of them individually is just to avoid clutter. Okay, the more the number of actions or predicates you have in your consecutive layers, and the more the number of edges you have to draw and maintain, and it just causes a bit of a clutter, right? So if you have the advantage of the goal sub goals being independent of each other, you can draw separate planning graphs for each of them, and that's what we are going to have a look at right now. Okay, so can you see this clearly? I can zoom in a bit. So what we are seeing is the planning graph for Amol. Okay. So here if you see, your P0 only contains the facts that were relevant to Amol, because this we are just drawing the planning graph for Amol alone. Okay, so you won't see any facts related to Aisha or Anisa in this graph. Okay, just for the sake of clarity. So your P0 has only one fact that was given in the initial state, that is Amol has 2 jabs or 2 shots of vaccine. Okay, and there is one nil fact in P0 that is basically coming because of this get appointment action that has nil as its prerequisite or nothing as its prerequisite basically. Okay, so is the P0 layer of this particular graph clear to everyone? Any doubts about the P0 layer? Okay, so nil basically indicates that this action in A1, okay, that's connected to this nil, which is get app a mole or get appointment a mole, that did not require any precondition, right? So what when we drew this such kind of an action, what we did was this get appointment a mole we wrote, right? And we didn't mark any incoming yellow edge into it because it does not have any prerequisites. You could also decide to mark a yellow edge, get appointment a mole, and just write nil, which basically means that this action does not require any precondition, or nil is its precondition. That's what is indicated over here by this nil. Okay, so if P0 is clear, let's now have a look at the A1 layer. This A1 layer, what this means is that the actions that you could apply given the facts in P0. Okay, and you see that the two actions that are very visible are the get appointment a mole action, which requires nothing as its prerequisite, so nil in the P0 layer, and it has one positive effect, which is hospital appointment a mole. Okay, which is a positive effect of this get appointment a mole action. That is one action you can apply. Another action is book Amol comma concert, which basically means that your Amol is trying to book the tickets for the concert, and it requires as its prerequisite the fact that Amol has 2 shots of vaccine, which is two jabs Amol. So that is shown by an edge between 2 jabs Amol and this action book Amol comma concert in your A1 layer. And this book Amol comma concert has one positive effect, which is ticket Amol comma concert, that is shown in your P1 layer. Okay, so these are the two actions that are from the set of operators that were given to you. Now if you notice that there are two slightly grayish dotted edges as well, right, from P0 to A1. So these are basically your no op actions, which I showed by that small yellow box, and here they are numbering it as 1 and 2. Okay, so basically in your A1 action layer, this this one that is shown by this dotted edge at the top, that basically means that is nil fact from P0 is being copied to your P1. Okay, so this one basically indicates one no op operator 1. Similarly, this 2 jabs amol also has a dotted line with a 2 in between, and then 2 Japsamol in the predicate layer 1 again. This also means that 2 Japsamol is being copied into your P1 layer through this no op operator called 2. Is that clear to everyone? Any doubts about it? Okay, that's great. So, yeah, basically, we drew our planning graph when we drew it by hand only till P1. Okay, if you go on constructing this planning graph, so once you have arrived at P1, again, you'll see the different actions that you could apply along with the no op actions, and that will form your action set in A2. And this dotted red edge between this in this A2 layer between book amol comma concert and attend amol comma concert, this basically indicates mutex relations. Okay, and if you'll see that in this P2 layer there is an incoming red edge. Okay, so that red edge is basically a negative effect. Okay, so if you complete this particular planning graph, if you go till the very end, you'll see that you had to make your planning graph up till P4, and in P4 you see that you have reached a predicate attending amol comma concert, which is the goal predicate you wanted to reach for amol. Okay, now that you have reached this goal predicate state, you will stop at P4. You won't make an A5 anymore. Okay, you have made P4 already. Now you will try to trace back your steps. Okay, so you'll see that attending amol comma concert, where is this coming from? Okay, so this has an edge up to uh, attend amol comma concert in this A4 layer. Okay, so which basically means that this attend amol comma concert action in A4 layer is causing attending amol comma concert in P4 layer. So you will add attend amol comma concert in your plan. Now you will see where is this A4 coming from. This A4 is coming from this ticket amol comma concert. Okay, this ticket amol comma concert again is coming from this book amol comma concert in A3. This book amol comma concert in A3 is coming from uh, where? 2 Japsamol. Okay, and this 2 Japsamol is basically something that has been carry forwarded through your no op actions from your initial state. Okay, so you can say that you have arrived at a plan for amol, which is to go from 2 Japsamol to book a ticket for the concert that resulted in this addition of this fact called ticket amol comma concert. And once you have this fact, you can then apply the action attend amol comma concert to get this fact attending amol comma concert. So if you recall, this also has only two steps required, or application of only two operators. Okay, we won't count the no op operators. So no op operators won't be part of your final plan. You only had to apply book amol comma concert and attend amol comma concert. And if you recall from the previous live session, Amol's plan was also consisting of only two steps, the optimal plan for Amol that we had found out. Okay, yeah, nice observation that we have reached P2 uh, in if we have reached attending Amol comma concert in P2 itself, but you see that there is a mutex relation over here, right? Okay, even if you consider the attending Amol comma concert in P3, that is a result of, let's say, attend Amol comma concert in A3. Okay, now that has to be a result of ticket Amol comma concert in P2. Okay, and that again is a result of book Amol comma concert in A2. So even if you choose to go that way, um, you will see that you are requiring two steps in your optimal plan. Yeah. In that sense, you could say that A4 and P4 are kind of not required. So I agree with you over there. Uh, yeah, maybe this has some redundant layers shown, but anyway, if as long as the concept of forming the final plan is understood, it's okay. You can stop when you reach the uh, attending a Molcoma concert. Or I think even better would be when you reach a particular predicate state that does not add any more predicates, any more newer predicates in your final predicate layer. I think that is the condition that you need to stop your algorithm on. Maybe I was mistaken, so sorry for that. My apologies. So if you see that in in this P3 and P4 layer, P3 and P4 are basically exactly the same, right? As some of you pointed out. Since P3 and P4 are exactly the same, that's why you are stopping at P4. If because no matter how much you go on adding after P4, you're going to get the same predicate layer. Yeah, that's what it is. So thanks for pointing that out. All of you who pointed it out in the chat box. Uh, Namita,
Sir, P2 and P3 is also same.
P2 and P3 is also same. Okay, let me check. Okay, we have nil, we have
From
hospital
P1
appointment.
P1 A2 to P5 A5 is the same, sir, in the term of concept. There's no
Okay,
change happening.
let us check that. You have nil, you have hospital appointment, a
No, no, the
mole.
last row. I was referring to the last row.
P3 and P4, you mean? Yeah, that we saw that those two have no change. Let us have a look at P2 and P3 as some of you pointed out.
Yeah.
Um,
Ticket double concept,
that is
attend double
there.
concept. Same thing.
Yeah, that is true. Okay, so that is there. But the issue with stopping at P2 is that here your attending Amol comma concert has a mutex relation, right? So it would be beneficial if you move one step ahead and see that there is no longer a mutex relation. Okay.
Okay, sir.
Yeah. Yeah. So to address your question in the chat, Namita, maybe it will be better if all of you actually could consult the pseudocode or the algorithm that is explained in the video lectures by Professor Kimani. Maybe he would have outlined the termination condition as in a much better way than I can recollect. Yeah. So from there you can check when you exactly have to stop your method. Okay. But what you have written does make sense. We can either stop when either the goal set has been reached or the graph is leveled off. That seems to make sense. But still, I would recommend that you check it once with the lecture slides or the lecture videos. That would be beneficial. Okay, yeah, and thanks a lot for pointing that out. That is something that I had also not paid attention to. So, yeah, thanks for that. Okay, so this was the planning graph for Amol, and as you see, it requires two steps in the optimal plan. Now let's have a look at the planning graph for Anisa. It's slightly longer. Okay, you can go through it. I've already uploaded all these planning graphs in the drive folder already. Okay, so you can have a look at it now itself or later if you want to. Um, Later on, if you want to have a look, then you can have a look later on as well. Um, this is the planning graph for Anisa and the final planning graph for Aisha also. Let's have a look at which is the most tedious looking, the most complicated looking graph. But yeah, if you just follow the steps, it'll be the steps will be pretty clear. Okay. Yeah, so I'm not going to the details of each of these for Anisa and Aisha because that will end up taking a lot of time. But it's already uploaded in the Drive folder, so I highly encourage you go through it and try to solve it by yourself, and then you can verify this particular solution given over here as well. And to address your query in the chat, Rocky says graph plan not guaranteed to find optimal plan. Again, I would recommend you check it with the lecture slides because I am not sure about it. So sorry from my side, but yeah, it's better if you check with the lecture slides. Based on the intuition, it seems like we might run into a situation. Okay, I think it depends on the. Yeah, I think it's best if you look at the lecture slides. Maybe Professor Kimani has touched upon it. Yeah, we will have to think about a case where graph plan fails to find the optimal plan. It will require some amount of thinking. So Sushant, you say that with the right tool, graphical tool provides better visibility and outcome. I guess you're referring to this in terms of your planning graph, and yeah, then I agree with you. Yeah, it does provide more clarity and visibility when you're trying to find your optimal plan. All right, so now let's circle back to our set of questions. Okay, so we started with the question that asked what are the different actions that will be present in the first action layer of the planning graph. Okay, this basically refers to the common planning graph for Aisha, Nisa, and Amol. And as you might have constructed by hand and from the individual planning graphs you saw, you can verify that get job one Aisha, get appointment Aisha, go Aisha, comma hospital, get appointment Amol, book Amol, comma concert, and get appointment Anisa would be all the different actions among these options given to you that will be part of the first action layer or A1. Okay. So I hope there is no doubt about this particular question. Is there any? P. Okay, so get jab 2 Aisha was not part of A1 if you remember, right? If I just revisit this slide, you won't find get jab 2 Aisha because we are not giving get Aisha the second dose of vaccine yet in the first action layer, right? So that is not part of the first action layer. Maybe it will appear in some later action layers. Okay, but this question asks us only about the first action layer. That's why we're not considering it. But yeah, thanks for your question, Sushant. Um, okay, now let's move on to the second question. Okay, so now that we have seen the whole planning graph, the next few questions won't require a lot of time. So, what is the number of actions, not counting the no-op action that is in the plan produced by graph plan? So, what do you think will be the answer for this one? So, remember, this is asking you about the complete plan for all the three agents, Anisa, Aisha, and Amol. Okay, will it be only 5? So if you recall, the plan produced by graph plan in this case is an optimal plan, right? And if you recollect from the previous live session, the optimal plan for Amol required only 2 steps. The optimal plan for Anisa required 5 steps. And the optimal plan for Aisha required 6 steps. So the total number of actions that will be required, not counting the no-op actions, will be addition of all of these. Okay, so 2 plus 5 plus 6, which is 13 exactly. Yeah, you're right, Mohan and Abhishek, and also all of the others who attempted. So 13 will be the total number of actions you need to apply in the plan produced by graph plan. Now, okay, sure, I'll explain once more. So if you see, if you remember, this was the optimal plan that we discussed in the previous live session. And if you have a look at the planning graph that we constructed today, or the complete planning graph that I showed you today in the solution that we had a look at a while ago, you'll see that there also the optimal plan for a mole required only 2 actions. Okay, and there also the optimal plan for Anisa required only 5 actions. And the optimal plan for Aisha required 6 actions. Okay, so 2 actions for Amol, 5 actions for Anisha, and 6 actions for Aisha. You add all of them up, that gives you 13. Right? 2 plus 5 plus 6 gives you 13. So in total, you need to apply 13 actions to make your complete plan for each of the 3 agents. Okay, so that was the total number of actions. But now the next question asks you, what is the make span of the plan produced by graph plan? What do you think will be the answer to this one? Six. That is correct. Namita, thanks for your answer. So it will be 6 because, so you see that you required 2 actions for Amol, but you required 5 actions for Anisa, and you required 6 actions for Aisha. So you will have to apply a maximum of 6 steps to complete your whole planning graph, whole plan, and you could sort of apply some of these actions for the different agents simultaneously, right? So you can't stop at 2, you can't stop at 5, you have to apply at least 6 actions in order for you to complete the whole plan, which is the longest or the maximum number of steps required by each of the agents that you want to solve your plan for. Make span means the uh, maximum of 2, 5, and 6 basically, the different number of steps required by your different agents. So the maximum of 2, 5, and 6 is 6. So you say that the maximum of your graph plan is, make span of your plan produced by the graph plan is 6. Okay. Finally, we are done with our graph plan method, and now we will have a look at our and or planning graphs. Okay, or and or graphs, not planning graphs, and or graphs. Okay, so a brief outline about and or graph. So basically, what you have in your and or graph is it depicts how a problem, okay, how a problem can be decomposed and transformed into some simpler problems. Sorry about that. So each of these nodes is given a name like S, A, B, C, D, and so on and so forth, and each of them has a cost included, which basically is a cost arrived at by some heuristic function or some heuristic estimate. Okay, don't worry about what that heuristic estimate is. You don't need to worry about that. The cost will be given to you in your and or problem. Now what you might observe is that, let me actually draw and explain it to you. Yeah, so you're starting with some problem S you want to decompose, and you have arrived at some heuristic estimate of the cost required to solve this problem S, which is 37. Okay, now what these three, so you see there are 3 sets of directions that this and or graph is going into from S. One is this direction towards A, one is this direction towards D, and one is this direction B and C. You see that there is a connection between B and C. So this connection basically indicates an AND condition, which basically means that if you try to proceed or if you try to decompose your problem S into A, you can you can either go for A, okay, then you'll further decompose A into something else and so on and so forth. Or you could go into the D direction, or you could go into the B and C direction. But if you go in the B and C direction, you have to solve both B and C. Okay, so if you have an edge like this, that represents and if you have something like this without this connection, that represents an or. So this basically means that you have three options to choose from after S, A, D, or B and C together. Okay. Is this particular and or graph definition clear? So Abhishek, which tiebreaker are you referring to? I'm not sure. Okay, so you mean that if you want to solve B and C, which of them you solve first? Okay, it doesn't matter. In order to completely solve S, you need to solve B and C, uh, to both of them, right? So you can solve either B or C. Okay, so that actually can depend on the heuristic value. Okay, when you see which of them is easier to solve first, or looks easier to solve first, you will solve that first. But actually, it doesn't matter because you have to solve both of them in order to get a final value for your S. Okay, so it doesn't really matter. Okay, so that was your and or graph. Okay, let's continue with the problem setting. Okay, so the number inside each of the node is a heuristic estimate of the cost of solving that node. The nodes in double circles like this one, L or M or F or G, H, I, N, O, K. These are all the primitive nodes or the ones that have been said to be already solved. Okay, so when you arrive at a particular primitive node or a double circle node, you say that we won't expand it any further. Okay, so that is your problem setting. And now let us consider that the cost of each edge is 1 unit. Okay, which basically what I mean to say is that when you decompose your S into A, let's say, okay, in order to solve A, your heuristic estimate says that we require 31 is the cost. Okay, and then if you want to construct S from A, you would need to add 1 to 31. Then your 37 will be replaced by 32. Okay, so each of these cost of these edges is 1. Okay, so given that, what the question asks us to do is we start with the node S and we have to expand it using the AO star algorithm. Okay, which is the AND or algorithm, AND or star algorithm. And we have to, again, you have to note that the primitive nodes are not expanded and we have to list the nodes in the order that they are expanded by the AO star algorithm. So let's start. Okay, let me start by, so we are at S right now. Okay, each of these edges has cost 1 1. Okay, now let's consider each case separately. So we saw that there are three possible directions we could go into. We could either go into A direction or D direction or B and C together. What happens if we go in A direction? If we go in A direction, we will have the cost of S replaced by 31 plus 1. This will become 32. Okay, let me draw it separately. If you go in your A direction, okay, as of now we are not considering what happens after A, only consider what happens till A. So A has a cost 31 given to us and this edge has a cost 1. So if we go in the A direction, the cost of S will become 32. If we go in the D direction, which has cost 37, the cost of S will become 38. If we go in the B and C direction, this has cost 20, this has cost, or this has cost 25 actually, and this has cost 20, and these are 1 1. So this will be 25 plus 1, 26, plus 20 plus 1. Okay, so 25 plus 1 plus 20 plus 1, which is basically 47. So you see that if you go via D direction, then also the cost that you are going to arrive at for solving S would be greater than what your uh, what is given over here in 37, right? So you would choose not to go in this direction. Similarly, you would also choose not to go in your B and C direction. But with when you go in the A direction, you see that it is reduced from 37 to 32. So you will choose to go in your A direction and then you will expand A next. Okay, so first you expanded S, then you expanded A. Okay, let me erase all of this. Okay, once you expanded A, again you have to choose from either E or F. Okay, if you go in the F direction, again these edges have one cost. Okay, so this will become 39, 38 plus 1, which is greater than 31. So which you won't choose to go in that direction. If you go via E, you will have 30 plus 1, 31, which is the same as A. Okay, so you will choose to go in the E direction. And since this is already 31, the cost of S will remain to be 32. Okay, so after A, you inspected E. Okay, so now when we inspect E, again we have two options to choose from, L or M. Okay, clearly M is the lower cost one because 25 plus 1, 26. So E will become 26. Because this became 26, your A will become 27, 26 plus 1. And because this A became 27, your S will become 28. And that will be your value returned by your AO star method for solving S. Okay. That is what is asked in the question. The nodes inspected in order are S, A, and E. List the value of the start node after every expansion. We saw that is 32, 32, and 28. Okay, so S became 32 when we expanded A, it remained 32 when we expanded E, and it finally became 28. And is the solution found by the algorithm the optimal solution? What do you think about this? We went in the SAEM direction. Yes, exactly. That's right. All of you have commented in the chat box. It is, yeah, is there a doubt? Okay, I see your message. You have asked to explain once again, right? Yeah. Is that what your doubt was? Hina, your voice is not audible, unfortunately. So maybe I'll mute you. And I'm assuming that you wanted the explanation to happen once more. Okay, it seems I cannot mute you, so I request you to mute yourself because that would help for the rest of the live session. Okay, let's see. Okay, so basically what we did was we saw in each step what are the different options we have. Okay, the one fetching us the lowest cost is the one we chose to go in. Okay, so for A it was 31 plus 132, so we chose to go in that direction. Then for B and C it was 47, which is 25 plus 1 plus 20 plus 1, which is greater than 37, so we didn't choose to go in that direction. Then D gave 37 plus 138, which is also greater than 37, so we didn't choose to go in that direction. We chose to go in the A direction, and then we further expanded along that direction. That gave us 28. Okay, but this is not actually an optimal solution, because if you have a look at this direction, okay, if we had gone in this direction, then we would have arrived at a much lower cost. So this would have given 12 plus 1, which is this would become 13. Okay, then this would be 13 plus 1 14 plus 10 24 plus 1 25. Okay, and sorry about that, 25 plus 1 26 is what we would have got if we had gone in this D direction, but we chose not to go in the D direction. Can you say what is the reason for that? Yeah, so Soundarya, to answer your question, whether your solution is optimal or not, that you can have a look manually by inspecting the different ways you could proceed in the graph. That's the only way. Yes, exactly. You are right. We have overestimated the heuristic value has overestimated the cost uh, uh, that is given to us in this AND or graph. Okay. Uh, so if you observe that, um, we chose to this cost that is given to us is 37. Okay, whereas it should have been lesser, right? So this clearly indicates that the heuristic function, whichever heuristic function we have used, has overestimated the value, and this AO star performs or gives the optimal solution when the heuristic function underestimates the value. Okay, so in the next example we'll see, let me erase all of this. We'll see that the heuristic uh, function has underestimated the value, the cost. Okay, so yeah, the question 6 answer would be no, it's not an optimal solution. Now let the cost of each edge be 10 units. Okay, initially we assume that the cost of each edge was 1 unit. Now if we assume that the cost of each edge is 10 units, now we will see that the heuristic function will be giving us an underestimated value. So now this is 10, this is 10, this is 10, and this is 10. Okay, so again if we go in the A direction, we will have value of 31 plus 10, which is 41. If we, sorry about that, if we go in the B and C direction, we will have 25 plus 10, which is 35, plus 20 55, plus 10 55. If we go in the B and C direction, and if we go in the D direction, we will have 37 plus 10, which is 38. Okay, so here we see that the heuristic value is lesser than all of these, right? So we have underestimated, the heuristic function has underestimated the cost now, and we will now choose to go in the D direction. Okay, so now the inspected node would be D. Now this has cost 10, this has cost 10. So if we find this particular solution now this will give us 17 plus 10 27 plus 10 37 plus 10 47. Okay, but this 47, we are getting now a lesser cost if we go in the A direction now, right, which is 41, which is lesser than 47. So we will switch back from going, initially we thought that we'll go in the D direction, but we see that if we proceed in the D direction with the edge cost 10, we will arrive at a non-optimal solution. So we will switch back and we'll go to A. Okay, so we'll now try the A direction now. So the nodes that we inspected were S, D, and now we'll inspect A. This will make S as 41, okay, which is the lowest among the options we have. And then we'll expand A. So this will be 40 and this will be 48. So we'll go in the E direction next, and that will change the cost to 30 plus 10, this will become 40, and 40 plus 10, this will become 50. Okay, so we'll proceed in that way, and if we complete the solution, we will find that the final solution that we arrived at was SADE were the nodes that we inspected. 41, 47, 50 and 55 were the different values of S that we arrived at. And yes, this is the optimal plan that we found out. Okay. How many decomposition in this? Okay, so to address one query before that, Namita, yes, from D it is 47, but if you proceed along that direction, you'll see that that is the final solution is not optimal, right? So the AND or the AO star method has sensed that. That's why it's staying with the A direction. And how to decompose? So the decompositions are already given to you, right? It's given in the form of this AND or graph. That will be given to you. What you have to do is you have to find out the final value of S. Okay. So unfortunately, we are at a shortage of time today. So it looks like we won't be able to discuss the additional questions today, but we'll discuss that next week maybe. And to address some questions before that, yes, you may use a tiebreaker over here. Uh, as far as I can remember, in case of a tiebreaker, you can choose to go in any direction. Okay, any of the possible options. But yeah, again, verify this with lecture videos, or you can post it in the discussion forum as well. That will be beneficial for all. And today we don't have enough time, but maybe we can go through this question again in the next live session if you want me to. So I hope that helps in your query, Vanshika. Um, right, Dr. Preeti. So thanks for the reminder. Yeah, maybe next session we can have an additional question on GSP. So we can discuss that maybe later on again. Okay. So yeah, thank you all for attending, and I hope this helped. And let's meet next week.